Good evening, good night, good morning, good afternoon, wherever you find yourself. Thank you for joining our fourth week of this major event. We are just absolutely thrilled to have you and to be sharing with you all of the content across our three tracks. Today we have some incredible speakers, a lot of female power today, which makes me really proud to see so many very competent and brilliant individuals in this field across all genders. But one of our organizers is going to be presenting to you on material science, and you all know her, Ali Henriques. And then we have another professor that's going to be walking you through KQD, which is one of the other hackathons that was presented by RPI, the Rensselaer Polytechnic Institute, as part of the IBM hackathons. And so, what I am going to suggest is that when you work through the content, right, we have given so many things that are optional. For example, we have stated that the badges that you can achieve on your own for QML or VQE or quantum chemistry, those are all optional for you. Even the quiz on fundamentals, it's optional for you. If you want to receive the participant badge, I mean, not badge, but certificate from IBM Qiskit Fall Fest, you will have to fill out a form that I'm going to be sending between today and our last day. Failure to fill out that form means you do not receive your participation certificate for IBM Qiskit Fall Fest. Hopefully, this is very clear. Everything else is optional, but if you want that, just registration will not guarantee that you are receiving this certificate. Very well. So we had an incredible week last week was the Quantum Week in Costa Rica, the first of its kind, and in two different universities. And then we had a virtual coffee where we talked about multidisciplinary research and different opportunities in the field. And there was also a gathering at IIT Ropar in India where the team went over some of the content and the workshops, and they have a couple of books that they're going to be distributing from our sponsor, Falcondale. Javier Mancilla, who you all heard at the first week of our event, he has a book called QML Unlocked. And so, depending on the location of the winners and the strength of the hackathons, some of the prizes might be that book or different scholarships depending on we're going to try to give second and third places a a representative award. However, it's the first place that we have the big awards for, like the Amazon bracket computing time, $1,000. So we have two of those. We have discounts for QECA certifications. We have some scholarships for certifications with EnLuz. We also have some books with Falcondale, the Applica certification where you could get the ethical hacking and different things that has been distributed in the Quantum Week in Costa Rica. So where are we today? We are in week 4 today in the IBM Tower in Buenos Aires, Argentina. Danielle Ruiz, who you have been hearing a lot about from the VQE and quantum chemistry track, is hosting that event with QNow and IBM Argentina. Our event in the Research Triangle Park is going to take place Thursday evening, and I will be sharing that invitation this afternoon. So if you are local and you want to join us, it's just a little happy hour kind of event where we can celebrate all the hard work that's happened, talk about some multidisciplinary research opportunities. There are a couple of papers and discounts at international levels that I have found that I think would be great if we can bring all of our incredible expertise together and do something new and something incredible. And so I will be there. I suspect Ali will also be there. And you might find other familiar faces from our event there as well. So more to come on that. And then where are we at the end? Last time we didn't get through all of quantum cryptography and KQD, and so today you're going to have a dedicated speaker on KQD. She is a very distinguished person, professor, and can't wait for you to hear from her. We're going to have the material science presentation, material science and quantum technology, which is like a next step of what is happening in the quantum chemistry field, other applications, and applications that have a lot of funding right now. That said, we are also going to be hearing from Mariano Caruso, who is from QNow, and he's going to be speaking to us on Wednesday about quantum security confidential Cubo solvers. And then I'm hoping that I can get two recruiters in. They're scheduled, first they were for Monday, then for Wednesday, and then I think we're trying to be flexible, but otherwise we're going to be sharing some of their opportunities in the Discord channel where the opportunity is. It says opportunities, oportunidades. Please keep checking on that, and we are continuing to share things that you can apply for. One of the things I also suggest is that because we have a lot of international folks, if you are looking for people to do research with, and you're maybe looking, for example, for a material scientist, for someone who's in neuroscience, or someone who is in chemistry, or someone who is, we sometimes are looking for an area of expertise. Last year, I was looking for an electrophysiologist, and I cannot tell you how hard that is to find someone who is an electrophysiologist that has applied AI and quantum. So that being said, we're going to have another section where you can also look for individuals that you would like to partner. Okay, so I'm going to uh, stop sharing here 1 second and then share the humanitarian challenge. At one point, actually, I do not need my video here. Okay. At one point, we had discussed this, and this is one of my favorite challenges because what it does is that it brings you to, well, it's almost like a meditative process where you can imagine that all of your needs are met and that all of the perceived and very real limitations that we have in life are not there. And then you think about your surroundings and you think, well, what would I solve and what kind of technology would I use? Does the technology exist? Does it not exist? How could I bring myself to think about solving these aspects around me that I'm passionate about? And so, for some reason, I can't find it. Just give me one moment. I'm just going to go to Discord. I know that's where it is. Okay, and one more thing I did here in our Discord was add a section with resources. I'm going to share my screen here. Yikes. Okay. Okay, so normally we are hearing announcements. And so last week we talked about cryptographic hash functions, and we went through some of the mathematical expressions and recommended mitigations for different types of algorithms. We talked about Shor's, Grover's, some of the ones that we could enhance at medium term. One of our interns is working on giving you some actionable things that can happen between now and 2030 when we are expecting to work through a peak post-quantum cryptography and different preparation because of the harvest now, decrypt later threat. And so this is a humanitarian challenge. And I just want to make sure you can see this. And it is make sure that I'm sharing the right screen. So it walks you through here, kind of like a visualization exercise. And the important thing here is that you can really take a moment, 5 minutes, to go through this. And so I was going to make a recording this year so you could just listen to it. But what's important about this is that you visualize the office space where you have unlimited resources. What does your dream office look like? You have unlimited resources, health, wealth, time, and you sit down to reflect. Is it a beach that you see? Do you see a forest? Do you see people around you? Is your family there and all the children and grandchildren are playing around you? What does it smell like? Does it smell like food? It's um it's important to engage all of your senses as you're going through this, and then you go through the steps, observing, defining, and start taking notes about these things. Like, are you typing? Um, are you talking to, I don't know, a future Alexa or something like that, and just saying, take note, or ChatGPT and having it summarize it. Just imagine how you would be logging this kind of information. And then at the end, your proposal, you can present a PDF or you can do a video. No more than 5 minutes, please. This is something where, we hope that you um, help your creativity unleash. AI is there now to do coding, presentations, a whole bunch of things for us. Don't outsource your creativity. Remember, this is your intellectual property. This is more for you to consider what you would like to address, and if we have current technology, maybe you might become passionate about creating something that can solve that for you. And so send me a video, a link to a recording. You could do it in Canva, you can do it in YouTube, you can create something. I'm not asking you to code anything, but talk to us about what you would be solving, how you would be solving. Do we have the current technology? Do we not? And then just put it in a 5-minute video. And we will be announcing those winners by Friday. We have this competition running in 2 different languages. The language for this is going to be English. So, because I got some in Portuguese and I'm asking them to pick English or Spanish. So please keep the submissions in English for this one. And then just send me humanitarian challenge in the subject and you will be in the running. And my email, I have added it in the Discord. All right, let's see what else. So before we introduce our next speaker, I want to show you one more thing. We have gone through a lot of the notebooks, and one of the reasons why we allow you to solve them is because when you are faced with that, you start understanding what you may know, what you may need to refine. And so the Qiskit fundamentals is here in English and in Spanish. The solutions are here. And you also have the DiVincenzo criteria and the solutions. For those of you that were present in person last week, we went through some highlights of the different criteria and why it's important. So keep an eye on that. And then I'm also going to be linking the hackathons over here, so you have resources. Some of the presentations, we have someone in charge of our GitHub, and they had something come up and they didn't finish the work. So I'm going to be uploading the PPTs and different things into our resources here for some of our speakers, so you have access to that as well. Sorry for the delay on that. I thought it was being done, and we have had to solve for a lot of things because life happens, right? So, all right, I'm going to stop sharing here and just double check if our speaker has joined us. Okay. I'm going to send her a message. Very well. Please join me in welcoming Dr. Swathi Mummadi. She is an associate professor in the Department of Computer Science and Engineering at B.V. Raju Institute of Technology, Narasapur, and an IBM Qiskit advocate and a postdoctoral researcher at the University of Malaysia, Perlis. She earned her Ph.D. in quantum computing and cryptography from the National Institute of Technology in Karnataka, and I'm sorry if I'm not saying this correctly, Surathkal, India. Dr. Mummadi has published over 30 research articles in reputed journals, her core conferences, and book chapters. Her outstanding contributions have been recognized through numerous awards, including the Young Researcher Award for her work in quantum computing, the KPIT Sud Award, and gold medal at KPIT Pune, and recognition as a finalist for the Quantum Rising Star Award and the Quantum Innovation Summit in Dubai. She has also received the Quantum Excellence Badge and Quantum Challenge Achievement from IBM, as well as Teaching Excellence and Gold Medal honors from her academic performance. A recipient of MATE-Y funding for a quantum machine learning project, Dr. Mummadi has also reviewed over 100 Sci-Index journals and conferences. Her research interests include quantum computing, quantum cryptography, quantum machine learning, blockchain security, advanced algorithms, and future internet architectures. With that, please join me in welcoming Dr. Mummadi, and you should be able to share your screen.
Yeah, thank you. Thank you so much for the introduction. So let me share the screen. Yeah, so is my screen visible?
Yes.
Okay. Yeah. So I'll start the session. So as like today we are going to discuss about quantum key distribution and its role in secure communication. So like let me explain you with the slides. Like we'll see what is the requirement of QKD and what is the problem we have been faced with the quantum computing in security perspective, and how to find the result by using the QKD that we'll discuss today. Sorry. Yeah. Yeah. So, so as I told you, today we're going to discuss about quantum key distribution and its role in secure communication. So let me talk about first of all what is the problem we have been faced with the quantum system and quantum principles. So like if you like, I think like most of you are already aware of like when a quantum experiment has been done on like using Shor's algorithm, it has been proven that like a Shor's algorithm can easily find the integer factorization, and it can easily break the 128 qubit 128 bit RSA algorithm. So like even in that experiment it has been proven that like it could able to break only in 200 seconds, whereas like a supercomputer will take 10,000 years. So that when we talk about this difference, like when a quantum system has been come into existence and when we start working with the quantum computing, the classical security will be in trouble, because most of the classical security algorithms are based on RSA and AES and many other security protocols we have. So once the system come into existence, all this will be in trouble. Like we can easily break this due to the quantum principles like superposition and entanglement. So I think most of you are already aware of all these quantum principles. So I'm not going to discuss in detail about the quantum principles. So today we are completely concentrating on quantum key distribution. So here, like in that experiment, they could able to break 128 bit RSA algorithm just in 200 seconds. So as I told you, when the experiment has been done, they have been claimed that it will take a supercomputer 10,000 years to solve the same problem. So this is due to the superposition where we can perform the operations exponentially faster compared to classical computing. So this is where the threat to the security has been understood by uh, like uh, the researchers and also the normal users. So this is where the research has been started in quantum computing, because like it has been like we already know that it has been 100 years of journey, like 100 years of quantum mechanics. But when this experiment has been done, then this the people who are working in quantum computing, who are working in computation has been shown the interest and they started working in quantum computing. But before that, most of the people used to work in quantum mechanics and quantum physics. So later on, like even with the availability of quantum systems, like cloud access of the quantum systems, like IBM and other companies are like they have been provided the cloud access. Then we had an opportunity to implement our own architectures and our own algorithms in real quantum system and also in simulator. So this is where the quantum like advantage of quantum has been understood by the most of the people. And if we see, like, so to overcome that problem, we have a solution is quantum key distribution. Like, as I told you, like in RSA algorithm, we will be having the prime factors, like we will use the prime factors for developing the algorithm. So if someone could able to find the prime factors, then it is easy for them to like break the algorithm. So to make the algorithm more safer, instead of classical keys, if we use the quantum key, then it is like it will be difficult for them to break because quantum keys are generated based on the quantum principles. Like even the quantum key is nothing but the qubits we are going to generate here. So which operates based on the quantum principles like superposition and entanglement. So the advantage of quantum information here is like it is no one can clone the data or no one can clone the quantum information because of no cloning theorem. So if someone tries to read the data or someone tries to clone the data, then it is easy to it is easy to understand because like if we are trying to clone the data, that is nothing but we are trying to measure the data. So once we try to measure the data, then automatically it will lost, like it will change, like it will be its actual state will get disturbed. So with that, the one can easily understand the modifications in the data. So that's why like at present, like till now, like we can say that quantum key distribution is one of the safest mechanism, and also like one of the security protocol or one of the security mechanism which can be used for developing the secure will be used in security. Okay, so let me talk about quantum key distribution first. So it is like quantum key distribution, as I told you, like we are going to transmit the quantum keys to secure the data. And when we are trying to perform the operations or when we are trying to transmit the data between sender and receiver, the data need to be more secured. So when we worked with the classical communication, we could able to see that like a third person can easily read the data, or like it is possible for them to clone the data. So, due to the quantum information, it is not possible for a third person to clone the data. Even if they try to do that, the sender and receiver can easily knows that like someone is trying to read the data, so that they'll cancel the communication and they'll start with the new communication. So this is the advantage of quantum key distribution. And like how third person intervention can be detected in quantum key distribution, that we'll discuss in detail with the like one example along with the diagram. So, like this QKD works based on the quantum principles, and as we know that like quantum data cannot be hacked or cannot be cloned, and basically all this like quantum bits whatever we are using in quantum key distribution are generated by using the photon particle. So all this like photon particle, the by default the nature of photon particle is nothing but whenever we'll perform the operations with the photon particle, it generates the noise. So at present when we are working with the quantum key distribution, like when we are trying to transmit the quantum keys between multiple locations, so the most of the people are facing that due to the internal noise there is a possibility of errors, so error rate is a little high. So the people who are working in quantum key distribution, they can also concentrate on noise mitigation or error. If they could able to add error correction along with the quantum key distribution, then key size will be increases, along with that the error rate will be reduces. Okay, so like we'll see how exactly it will be done, but before that we will see like what are the different quantum key distribution protocols we have, and then we will see the basic protocol, that is BB84 protocol, in detail along with an example. So, if we talk about the advantages of quantum key distribution, we can use quantum keys in wherever we require the security, especially in healthcare and also in government. If we talk about the military or defense, we need the secure communication channel. So, there to secure the data, we can use the quantum keys instead of the classical keys. And also, we can use it in finance, and also we can use it for the data protection wherever we require. So these are some advantage, like some applications of quantum key distribution. But apart from that, there are many other advantages with it, and it has very important role in secure communication. So we'll discuss about all this in detail in coming slides. So these are some QKD protocols, the basic protocols we are talking about. So here, the first protocol which has been introduced is BB84 protocol. So it has been introduced in the year of 1984 by the by Bennett and Brassard. So based on their names, the name has been given as BB84. So in this BB84 protocol, they have been used it for the to transmit the data or to exchange the data by using the cryptographic keys in terms of quantum data. So here, what they observed here is when they used quantum keys for data transmission, they could able to see that, like, if any third party tried to read the data, or if any eavesdropper tries to observe the data, they could able to easily find out that. So how that has been done, we'll discuss. But here in BB84 protocol, they have been used horizontal, vertical, and diagonal polarizers for transmitting the information. So here, they used to, 0 degrees and 90 degrees were used for the horizontal and vertical, and for like positive 45 degrees and negative 45 degrees were used for the diagonal polarization. So whenever through that polarization, if whenever the photon particle has been transmitted, accordingly the data used to be generated, and that data will be transmitted to the receiver side. Okay. And next, in the year of 91, the Eckert 91 protocol has been introduced. So in BB84 protocol, we are working on quantum random number generator, where the sender and receiver randomly, sender randomly sends the data using different polarizers, and even receiver receives the data using different polarizers. So it is completely randomized randomized key distribution protocol. And when we talk about the ECART 91 protocol, here they have been used bell representation, nothing but they have been used entangled qubits for to transmit or to distribution. So even like when we compare it with the BB84, it is different, because here we will be having some entanglement generator. It used to generate entangled qubits, and those entangled qubits will be transmitted at sender side and also the receiver side. So we used to have entanglement generator like this, and entangled bit, one bit will be transmitted here, one bit will be transmitted here. So we used to have bell measurements for measuring the data and also for transmitting it multiple parties. And now coming to the the other protocol we have here is B92 protocol, so which has been modified version of BB84 protocol. In BB84 protocol, as I told you, like we had horizontal vertical for representing state 0 and state 1. And we also have the positive diagonal, negative diagonal for representing state 0 and state 1. So there will be two representations. That means when we consider horizontal vertical, again there will be two representations, and also in diagonal there will be two representations. So total four possible representations can be used for transmitting the data, right? So with this, what happens is, like, there will be to make it more easier, these four representations have been converted into two representations. Either it can be horizontal or vertical with 0 degrees or 45 degrees, or like diagonal, we can say. So this is the modified version of BB84 protocol. So it has been introduced in the year of 1992. So here they used to use either 0 degrees representation or 45-degree representation for generating the qubits, either state 0 or state 1. So this is about the basic quantum key distribution protocols. So now we'll see in detail about BB84 protocol. So yeah. So before discussing in detail about the BB84 protocol, so first of all, let me explain you how qubits will be generated, because in use the different polarizers. So first of all, sorry. So in this, first of all, to generate a, like in quantum key distribution, there are two methods. Like one is quantum key generation, and second one is quantum key distribution, right? So first of all, to generate a quantum key, a key can be generated by using the a light beam. So a light waves will be in unpolarized representation because it will be in multiple directions, right? So to make it as a polarized one, we will transmit, like, the light beam will be transmitted through the polarization particles. You can see this. So through this polarization particle. So we have different types of polarization particles. It can be horizontal, vertical, or diagonal. So through whatever the polarization particle it has been transmitted, accordingly the light beam will be polarized. Okay, so that polarized light beam will be considered as a qubit, and that will be transmitted from sender to the receiver. So this is how a qubit will be generated. And like, if we talk about the polarization basis, as I told you, there will be different polarizers. We can either use horizontal, vertical, which we'll call it as a rectilinear basis, or else we have diagonal basis, which is called as a positive diagonal and negative diagonal, as represented in this diagram. So according to this, like, in rectilinear polarization, the horizontal can be represented as state 0 and vertical can be represented as state 1. So it depends, like, how the algorithm has been implemented. Accordingly, we can represent the horizontal as 0 or vertical as 1, or vice versa. And also in diagonal polarizer, we have the positive diagonal and negative diagonal. So positive diagonal again can be used for the, if you see, so the positive diagonal can again used for the state 0, and negative diagonal for the state 1. So this is how the bits will be represented and also will be generated. And accordingly, the algorithm will be implemented for quantum key generation and also for the distribution. So this is like how polarization will be used, because when we talk about the quantum key distribution, one need to understand how quantum key will be generated. That is also very, very important. If we are unable to understand the key generation process, then it will be difficult. So as I told you, in key generation process, there will be two methods again. We can either use quantum random number generator, which is called as QRNG, or else we can also use the entangled based quantum key generation, like where we use the Bell measurement. So entanglement based quantum key generation also can be used. So this QRNG, like we are talking about BB84 protocol, so here they have been used QRNG, random number generator. So if we talk about Eckert 91 protocol, then there it has been like entangled based key generation has been like used. So this is just introduction to the BB84 protocol. Now we'll see in detail about BB84 protocol, how exactly the key will be transmitted. So let us see, like, this is the process how a BB84 protocol will be will be used for transmitting the data from source to the destination. Let us say we have a source, or the sender Alice, and the receiver Bob. So now if Alice wants to send the data to the Bob, so what happens, like Alice, like here we are talking it as a, like, quantum key distribution is one of the safest mechanism, and at present it is 100% unhackable. So like if anyone try to hack the data also, it is easy for the sender and receiver to know that. So how they could able to know that, that we'll see. So now Alice will send the data, and the data will be sent in terms of the qubits. So for that, again, we need to use the polarization particle. So now at Alice said they have the light beam, and that light beam will be transmitted. So this is unpolarized light beam. So that will be transmitted through the polarization particles. So based on so whatever the polarization particle has been used, accordingly the data will be transmitted. So here Alice randomly uses the polarization particle. He may use the state 0 or state 1, like, sorry, he may use the horizontal or vertical or diagonal, like positive diagonal, negative diagonal. So he will not say that to anybody while sending the data. So let us say the first, this is the first bit which has been transmitted from the Alice to the Bob. So here he has been used the diagonal. You can see this. So he has been used the diagonal representation. So this represents the bit 0. So that 0 has been generated through the diagonal representation. Okay. And then next he wanted to transmit the state 1, quantum state 1. So for that he has been used the like horizontal, like this polarizer. You can see this. And then if it like next day has been transmitted 0 with the again diagonal polarizer. and again he has been transmitted one using the diagonal polarizer. So all this he has randomly used. So he thought like at that particular time whatever he thought of transmitting, that he has been transmitted through the random polarizers. So now the data has been transmitted. So if you see here he has been transmitted, all these bits to the Bob. Now like data has been transmitted, so this entire representation, like this entire the channel, we can call it as a quantum channel, because a quantum data cannot be transmitted through the classical channel, because as I told you, like quantum data, quantum states are different when we compare to the classical bits. So for that, like we need to have a separate quantum channel where the data will be transmitted safer. And even while transmitting also, there is a possibility of getting errors due to internal noise. So we'll see that, like how to overcome that problem. But before that, now Alice has been transmitted the data through the random polarizers he has been used, and now the data has been transmitted to the Bob through this channel. Now at Bob's side, Bob need to read the data, right? So he has to understand what Alice has been sent. So to understand that, first of all, he need to measure the data. Let us say to measure the data, even Bob uses the random polarizers, because Bob doesn't know what Alice has been used for sending, right? So now Bob randomly uses. You can see here, these are the bases Bob used. Okay, so these are the bases the Alice has been sent. So now, so for the first bit, to read the first bit, Bob has been used again a diagonal basis. So even Alice has been used the diagonal basis, so both are matched. So here the bit will be same. And for the second bit reading, to read the second bit, even Bob has been used horizontal, vertical, or rectilinear. So even like this also matches. Now the third bit, like third bit has been transmitted. Like Alice has been used diagonal, but if you see, Bob has been used rectilinear. So here the base is changed. The base is different, right? So even though the bit, whatever they have been measured, even if same, if matches also, it doesn't matter here. It only matters with the polarizers what they have been used, because why it is matter, like that I'll explain now. Explain later. So now even here it has been used. Like see here, so diagonal, but Bob has been used like rectilinear, so here it will not be considered for the key. And if you see the third bit, so for the third bit he has been used diagonal, Alice has been used diagonal, and even Bob also used the same polarizer, so it will be considered. And similarly next similar, so this is how the data has been transmitted from Alice to Bob, and Bob has been measured in different bases, so he also randomly used bases. So now, after transmitting the data and after Bob reads the data, now they will make a classical channel, like they will contact through the classical channel. So this classical channel can be either through phone or through the WhatsApp or through the mail. So they will communicate. So in that communication, now what they will discuss is, like they will not talk about anything, like any data, or like they will not talk about the data. Simply, Alice says that what polarizers he has been used for sending the data. So simply the polarizer details, because now nothing is there in quantum channel, because the data has been transmitted from the Alice to the Bob through the channel. Now nothing is there in the channel. Even after revealing the polarizers also, there won't be any problem. So that's why now Alice shares what polarizers has been used. So now based on that, Bob understands, okay, so the polarizers which are matched, only those will be the key. So according to that, they will check this. So now that's why, like if you see here the polarizer is not matching. Sorry, here, yeah, here diagonal and here rectilinear, but polarizer is not matching, but the data is matching. So they are not concentrating on the data, they are concentrating only on the polarizer what they have been used. So if polarizer matches, then only they'll think that okay, the data has been matched. Otherwise they will just simply discard that particular bit. So this is how, so this is, so these are the bits Alice has sent, and these are the bit Bob has received. But now, based on the polarizer, wherever that particular polarizer has been matched, only those bits will be considered as a key. So even though like it has been transmitted lot little more data, but like 12 bits of data, but the final key has been represented, or like the final key we got here is with 8 bits. So this is how BB84 protocol works. So now, what if a third person try to read the data? Because we said like in BB84 protocol, even if a third party tries to read the data, a sender and receiver will can easily know that. Like how they could able to know that, that we'll see now. Let us say while transmitting, like when Alice has been transmitted the data in between, let us say Eve try to measure the data or try to observe the quantum information. So what happens? Let us say the first bit. So Alice has been transmitted, but in between Eve has measured the data. So what happens? So first Alice has been transmitted through the diagonal basis, right? So now let us say Eve has been used. So because even Eve doesn't know which basis Alice has been used, because Alice is not shared with anybody until the data has been transmitted completely to the Bob. So now simply Eve uses the random polarizer. Let us say he has been sent through the diagonal. Let us say Eve has been used diagonal. Then no problem. The data will not modify. So the same will be transmitted to the Bob side. Let us say the second bit has been used is rectilinear, but used again, let us say diagonal polarizer. Then what happens? So actual shape, like actual the data we have been represented is with rectilinear, but Eve has been used diagonal. So with this, what happens? The qubit will get disturbed because it is not the actual polarizer through which Alice has been sent. So now the state of the qubit will modified. So this horizontal, when we transmit through the diagonal, its state will get modified, and that modified data will be transmitted to the Bob. So this is how the process will be done. So all these bits will be transmitted from Alice to the like Eve, Alice to the Eve, and Eve randomly uses some polarizers. And after reading the data, like the data will be transmitted to the Bob. So after transmitting all the information, so now, as I told you, Alice and Bob will discuss through the classical channel, right? So when they discuss through the classical channel, they can understand that even after using the same polarizer, also they could not able to get the same data because the bits are changed. So that is due to the third party intervention. Because if there is no modifications in between, then there is no possibility of changing the data. If they use like if they both use the same polarizer, obviously the data, the final outcome must be the same. So if it is changing means there is some third party intervention. So what they'll do is they simply cancel this transmission, like cancel this key distribution, and again they restart with the new process or restart with the new key transmission. So this is how a data will be transmitted using BB84 protocol, and this is how it is safer and 100% unhackable, like because of the qubits which are developed using the like quantum principles. Okay, so this is about BB84 protocol. So if any of you are having the doubts, we can have a discussion on this, because this is the basic quantum key distribution protocol. Based on this, the currently people are working on many other new protocols for the to overcome some issues that we are having in BB84 and to improvise that to the next level. Okay, if there are no questions, we can move to the next slide. So now this is how a quantum key distribution works. Now we'll see what is its role in security. So mainly, as I told you, like once the quantum systems come into existence, the classical security will be in trouble. So we need to make it as a quantum safer. So for that, we can use the quantum key distribution, because now security protocols rely on public key and private keys, right? So if someone knows about these keys like private key and public key, then it is easy for them to like hack the data, or they can easy for them to observe the data. So to overcome that, instead of using classical key, if we use the quantum key, then we can provide unconditional security, because as we know that like in like we can't try to hack the quantum data. Even if we try to do that, then it can be known by the sender and receiver. So that's why it can be used in unconditional security. And at the same time, it can also be used to detect the eavesdropping automatically, like as I told you in previous example. So it can easily, like we can easily detect the eavesdropping problem, because if anyone try to read the data also, like even if anyone try to measure the data, so measuring is nothing but we are disturbing the state, quantum state, right? So when we disturb the quantum state, that disturbed data will be transmitted to the receiver side. So then, after discussing sender and receiver through the classical channel, it is easy for them to understand. Okay, like some intervention has been happened, so we will cancel this transmission. We'll restart the new transmission again. So this is how it can be used for detecting the eavesdropping, and also can be used for like generating the random keys and secure keys, as I told you. So in quantum key generation, there will be different methods. Like either you can use the quantum random number generator or entangled based quantum key generation. So where we'll use the Bell measurements and all. So you can generate which are of highly random. Like when you develop the quantum random number generator, you need to get the like you need to get tested by the you need to send it to the NAST for checking how your key like how your algorithm is providing the random numbers and how randomized it is. So based on that result, you can say that like whatever the new algorithm you have been implemented for the quantum random number generator is actually gives the randomized data, which is not possible for a third person to hack. So like you can also think in that way for continuing your research in quantum key distribution. And also we can generate the fresh keys like which are in terms of quantum information. And apart from that, we can also protect the quantum system against the threats, because like and also like as we know, quantum data is safer, but once the like quantum systems existence like come into the existence as we're using as a classical system today, then classical security will be in trouble. So to make it quantum safer, we can use quantum key distribution in classical security protocols, and by making it as quantum safer, and with that it can we can easily make it as a like we can easily protect that from the quantum threats. So that also where we can concentrate on. And then we can also integrate with the classical security systems. So when we talk about the quantum key distribution, like there are two ways. Like when we talk about the cryptography, so quantum key distribution plays an important role in quantum cryptography, right? So this quantum cryptography has came into existence by seeing the threats that have been posed by the quantum computer. So to overcome that, we are working on the quantum cryptography where we are developing the quantum safer algorithms. But at the same time, like all these quantum cryptography protocols or algorithms will be implemented on quantum platform, right? So, but at the same time, what we can do is we can also make classical security protocols into quantum safer. So how we can do is like all classical security protocols are developed by using the classical perspective, like classical information perspective, right? But if we think in quantum perspective, and if quantum system will be used for breaking the classical security protocols, then we need to modify the classical security protocol math like algorithms. Like we need to make it the complex, like we have to add complex mathematics to make it more stronger and also the safer from the like quantum threats. So there we can integrate classical security systems with the quantum principles to make quantum principles. And this is where like the post quantum cryptography will work. Like this is how a post quantum cryptography process will work. And next, we can also enable ultra secure communication networks. So, like even to develop the quantum networks, like we need to use the quantum key like quantum keys. So, with the help of this, we can develop the even more secure quantum like communication channels, and also it will be like essential for the future quantum internet. So when we talk about the quantum internet, we need to have a quantum networks, and even we need to transmit the safer data through that network. So if we use the quantum keys, then I mean that will be one of the safer data transmission can be used in quantum networks and can be used in quantum internet. So these are the roles how quantum key distribution will be used to strengthen the security in various perspectives. Okay. So these are the advantages, but at the same time, there are some challenges which we need to concentrate on. So the major challenges here is the first one is error correction. So as I told you, like when we try to transmit the data through the quantum channel, so when we transmit the
Cuando
qubits through
tratamos
this.
de transmitir la corrección,
Hello. Yeah.
if you
So when
could
we
hear me,
transmit the
that was an
data.
error with the translation. I'm sorry. Let me pause this. Go ahead.
Yeah. Okay. Thank you. So when we transmit the data through the channel, so automatically it has to interact with the external environment. So that leads to the noise because by default photon particles will be prone to the noise. So this noise will leads to the errors. So that's why, like, whenever we'll do the quantum key distribution process, there is a possibility of getting a lot of errors. So even there are some cases without intervention of third party, also the data will be modified, like will get modified that due to the internal noise. So in such cases, the sender and receiver thinks that some third party has tried to observe the data, but it is not actually. So it is due to the internal noise. So for that, like if we could able to integrate error correction along with the quantum key distribution, then the results will be far better compared to what we are seeing today. And also the key rate will increases and error rate will be reduces. So the first challenge is integrating error correction with the quantum key distribution. So that we need to concentrate on. And apart from the noise, we also have one more challenge, that is decoherence. So usually a quantum data is represented in Hilbert space. So we will be having a Hilbert space of 3 dimension. Okay, so whenever if I wanted to read the data or if I wanted to measure any quantum state, it must stay in this Hilbert space. You can see this circular bar. So if it is not if it is not having any coherence in this Hilbert space, then the data which we have been stored in that particular quantum state will get lost. So, so that's why maintaining coherence is very, very important. But due to the internal noise, the coherence may be weakened. So that may leads to the decoherence. So decoherence is nothing but losing the data. So due to these two things, like the error rate will increases and also the key rate will reduces. So we can even try to think how to integrate error correction along with the quantum key distribution. So actually, this was my research area when I was doing PhD. I've been developed error correction, and that have been integrated with the quantum key distribution, where I could able to see very good results compared to without error correction mechanism. And next, we have one more challenge is qubit coherence time. So whenever, like if we wanted to transmit the data from sender to receiver, it has to live for at least for some longer time so that the data will be transmitted and will be received by the Bob, right? But the major problem in quantum information is coherence time because qubits are generated from the different materials, like we have the different superconducting material and we have ion based material, silicon based material and photonic based material. So based on what material you have been used, accordingly the coherence time also changes. Okay, so even like at present the problem we are facing is with coherence time. So qubit can be live for some period of time, so within that time we need to perform the operations. So after that, its coherence will be lost, nothing but the data, whatever we have been stored, will be lost. So if we could able to increase the coherence time of a qubit, then automatically the data, whatever we have been stored, will be will stay for longer time. So we can also concentrate in this particular area to increase the coherence time. So in this, if you wanted to work in this area, you need to work at quantum materials. Like you need to work at material level, and you need to see what are the materials we have and which one will give the better coherence time, along with the high fidelity also. So even coherence time is not only the thing; we also need to check whether it is giving high fidelity or not. And then one more challenge we have is specialized hardware requirement because the hardware the hardware required to perform to experiment on quantum computing, or let us say quantum machine learning, quantum key distribution, we require the hardware which is of high cost. So even we require the scalable and also reliable quantum processes, so which are little difficult in particular point of time, and spending a lot of money for, sorry, so spending a lot of money for the quantum hardware is also again a major challenge. And one more challenge here is algorithmic complexity. So so the algorithms, whatever we are designing, will be of little complex because all these are also integrated with the mathematical modeling. So you need to explain each and every concept along with the mathematical modeling, and also to develop the algorithms for the new methods. The complexity, it depends on the complexity, so it increases that. So if you could able to develop the algorithm, sorry. Yeah. So, and the major one more challenge we can see here is skill gap. The people or the students, or let us say the manpower required in quantum research, should have, excuse me. Yeah, just give a second. So sorry. Yeah. So to continue the research in quantum area, we need the skilled persons like who are good in quantum principles and also quantum algorithms. So at present, we could have we could see some skill gap. So even the people who started working in quantum has been increased when we compare to the earlier days. So these are some challenges and limitations we have, like we come across when we started working with the quantum key distribution or quantum quantum computing research. So if someone looking for the future directions, so it is not only related to the quantum key distribution. I'm just talking about the future directions of quantum research. So in quantum, we have the various domains, like we have quantum computing, quantum cryptography, quantum machine learning, and quantum optimization, like quantum architectures. So there are various areas which you can concentrate today. So there are the future directions where you can concentrate on, like the first thing is like quantum hardware advances, where you can concentrate on developing the quantum hardware which will be the scalable and also the error free, or which can be associated or integrated with the error correction mechanism. And the next thing you can concentrate is on new algorithmic design. So you can develop the new algorithms for various applications. It can be for quantum machine learning models, or it can be for quantum security, or it can be for the even like it can be for the finance, or it can be for logistic optimization. So you can also work on developing the new algorithms for the high accurate results when we compare to the classical computation. And also you can concentrate on hybrid models where you can integrate classical and quantum computing. And also you can concentrate on applications like climate modeling, robotics, and also weather forecasting and autonomous systems. Like there are various applications and broader applications where you can apply quantum for the better results, compared to the classical computation or what we are seeing today. And also you can concentrate on standardization frameworks, like where you can establish the startups, and where you can even go for the patent publications and patent grants. So these are the future directions if someone wants to start their journey in quantum computing or wanted to continue in their journey in quantum computing. So it not only related to the key distribution and can be applicable to all the areas of quantum computing. So quantum key distribution, like if we wanted to more specifically the quantum key distribution. So even you can apply quantum key distribution in all security protocols, like to strengthen those protocols and also to make it quantum safer. So that's all about the presentation today. So if anybody have any doubts, you can ask me. Later on, we can see the hands-on implementation.
Thank you, Dr. Swathi. Do we do have a question here. So what's
Yeah.
the bare minimum to apply for a PhD in post-quantum cryptography? Does it require a master's in physics or mathematics, or a person with software background, programming, and security knowledge can also apply?
Yeah, the people as just or quantum computing or quantum key distribution is a combination of classical algorithms and also the quantum principles. If someone could able to understand the quantum principles in detail, and if they are good with the classical crypto systems like quantum security protocols, they can apply rather than the background. Like if they are physics student or chemistry, or they are physics or mechanics or computer science, or like even software engineers, if they wanted to shift their the work from classical security to the quantum security, they need to be strong with the quantum principles first of all. So without understanding the quantum basics, no one can work in quantum computing, and it will be difficult for them to continue the journey. So I suggest, like, rather than a background, if you are interested, you can start your journey in this. But only thing is, you need to be perfect with some mathematical modeling. So you need to be perfect with some mathematical, linear algebra, and we have the complex number system and probability and statistics. And then, if you are strong with, if you are confident with the quantum basics like superposition, entanglements, and quantum principles, then you can start your journey in this.
Wonderful. Thank you. Let me see if there are any other questions. I like to tell folks that that everyone is becoming an expert simultaneously because
Yeah.
it's an emerging field, and that's the beauty of it, and that's what allows so much opportunity right now. Um, so okay, that is the extent of the questions that we have live right now. Usually we have a lot of folks that listen to recordings because of the timing and the differences in time zone. So
Correct,
I
correct. Yeah.
I might reach out to you if there are any other questions. But we really thank you for your time, and that was a breath of knowledge. It's very interesting when I explained this topic with gossip, and I had people trying to eavesdrop. It was all cartoons, and I was trying to get them to understand that the change in phase and shifting the phase and the Z gates and all of that, how important it was to understand that sort of thing. But your in-depth explanation with the polarizations is exactly what we needed. So thank you very much. And
Yeah.
there is a request for
So
your slides,
actually,
but go ahead.
yeah, yeah. So actually, I thought of explaining this with the hands-on, the implementation also, but due to the time constraints, I could not able to. So at least we need 30 more minutes for to explain how to write a quantum key distribution, like how to generate quantum keys and quantum key distribution between multi parties in Qiskit platform.
Mhm.
But we'll see, like if next time we can catch up with
If
the
you are
implementation
open
also.
to it on Wednesday, we have some time. I'll send you some time slots to see if it works for you. And if not, we could do a recording and distribute it to the attendees as well. So that can also be at your leisure rather than in these time slots. So the people are very grateful. They say thank you for your excellent explanation on Alice and Bob, and some people are asking for the slides. So it's up to
Sure.
you. So if you can send it, we
Yeah,
are
yeah,
posting some of the slides in our shared cohort if you are comfortable with that. And I'll send you some options for the for Wednesday while we close our program on that day. But if there are no more questions for Dr. Swathi, we will let her get to bed. Thank you so much. And
yeah.
and we will be hosting a couple of hackathons. This is a great basis for them to be able to do so. And we hope to collaborate with you in the future. If you have any opportunities or you're looking for students or researchers, please don't hesitate to reach out so we can continue sharing them in our Discord platform.
Sure, sure. It will be my pleasure. So, like, it was a night, like, I was, first of all, thankful to you for giving me this opportunity. So, it was a great platform where I can, where I can share my thoughts with the people around the world. So, thank you for that. And we'll see the possibility of continuing the session on Wednesday. So, we'll discuss
Sounds
on
good.
that.
Thank you very much for your time and expertise. I'm going to apologize for my video not working. I cannot
It's
seem
okay. It's okay. No problem.
I can't seem to make it work. This week with the electromagnetic storm, we've had recordings pop in and out of existence. Translation, I got kicked out just randomly. So, we're just going with it. At this at this point, I'm like, oh, well, I'll have to translate this later. So, no problem.
Yeah.
Okay, so let me share my screen, folks, and let me introduce you to our next speaker, who, interestingly enough, Dr. Swathi is going to be talking about material science and quantum technology. So let me share over here. All right. It is my pleasure to introduce one of our co-organizers for this event, Dr. Alexandra Henriques. Ali has worked at the intersection between government and science, helping technology companies and researchers secure funding for research development and scale up. She has worked with clients in a variety of industries, including artificial intelligence and machine learning, pharmaceuticals, and medical devices, green chemical manufacturing, electrical grid infrastructure, semiconductors, and advanced electronics, and quantum computing. Ali obtained a Ph.D. in material science and engineering from the North Carolina State University, where she collaborated on multidisciplinary projects with faculty and students both domestically and internationally. For her dissertation research, Ali studied the atomic structure of piezoelectric and ferroelectric materials. She will be presenting on material science and quantum technology. So, Ali, thank you, and take us away.
Thank you so much for the introduction. I will pull up my screen now and we can get started. Can you see my screen?
Yes.
Yes, ma'am.
Excellent. Thank you. All right, so as Melia mentioned, my name is Ali Henriques, and I will be speaking with you all today about the intersection of material science and quantum technology. To get started, a quick outline of what I'll be covering in the talk today. I'll start out with some fundamentals of material science and engineering just to make sure that everyone's on the same page, given we have attendees with a pretty diverse set of experiences and backgrounds. Then I'll discuss a little bit about the history of computational material science and how that is evolving into the use of quantum computing for materials research and discovery. I'll talk a little bit about how the inverse also is true, how material science is enabling quantum technology, and then get the discussion started on next steps in the field. So without further ado, what is material science and engineering? I will give the initial caveat that it is highly interdisciplinary as a field, spanning the range between chemistry, physics, engineering fields, data science, and more. So as we think about that, I guess I wanted to make sure that you all know that yes, this is definitely related to physics and some other fields, and it's sort of a niche focused specifically on the materials themselves. So we sometimes like to categorize this into material science and materials engineering, where material science is focused more on researching and studying the impact of structure of materials on their properties and focused on the development and discovery of new materials, whereas materials engineering is more focused on designing material structures to obtain the desired properties and performance, It also involves developing techniques for processing of materials and creating products and systems with the correct choice of materials. So in all of these different facets, there's opportunities for a computational approach to be used. So you'll notice on the left side, there's a diagram that is the traditional materials tetrahedron. So just as a quick overview of what this means and why I'm showing it, it's an illustration of the relationship between these core facets of material science and engineering as a discipline. Mainly in this talk and in general, we focus a lot on the structure and properties in the material science research space. So the interplay between how everything from atomic structure, lattice structure, uh, molecular bonding, chemical bonding, and then higher range ordering, so microstructure, macrostructure, can impact the properties of a material. So this spans everything from mechanical properties, electrical, optical, chemical properties, corrosion resistance, magnetic behavior. So think big when we're talking about materials properties. And then the remainder of the tetrahedron of processing and performance are all interconnected in that they all impact one another. So the structure by necessity impacts the performance of your materials, the processing of the materials give rise to the structures that we see at all length scales, and that in turn impacts properties and performance. And then at the center of all of that is characterization, which is sort of the basis historically of analysis of our materials. And this also feeds into a computational, whether it's classical computation or quantum computation approach to how we think of our material properties and how we assess our materials. So I personally tend to do really well learning about things when I think about it in terms of an example. So I wanted to start out with an example material that's pretty near and dear to all of our hearts. Whether we're thinking about it or not, it is near to all of us at any given point in time in this day and age. So with silicon, if we're thinking about the structure, the picture in the top right is just raw silicon in its pure form. But when we think about silicon in our devices for microchips, it definitely takes a different form. There's processing steps that go into making silicon useful for our computers, characterization that takes place to make sure that we understand what we have made, why the properties that we have are existing in the system. Um, the atomic structure of silicon is part of the reason why it's so useful as a material in devices the way that we use it. Um, in contrast, our next example material, diamond, is really interesting because it actually has the same atomic structure as silicon. They're both diamond cubic lattice. However, we think of diamond for largely its hardness, the fact that it is one of the hardest or the hardest substance. But in addition to its hardness, diamond has really interesting properties because although it's carbon just like graphite or graphene, the bonding gives rise to different properties. So it is a very good electrical insulator. It has high resistivity, but very unusually for electrical insulators, it actually is an excellent thermal conductor. So it can dissipate heat very quickly. And for that reason, the image on the left is an X-ray tube. It's actually used because diamond is transparent to X-rays as a window in X-ray tubes. And this in part is because it is both an electrical insulator, which is needed for that application, but also a thermal conductor to dissipate that heat. So sort of a really interesting material, even just outside of our conventional use or thinking of how we could apply that. So, sort of the crux of thinking about material science, materials discovery, both historically and today, is we're trying to make advances in society, and a lot of our civilization has been defined by the materials we use. Starting with the Stone Age, Bronze Age, Iron Age into the modern day, a lot of our modern technology hinges on the materials that we use. But how do we continue to improve and accelerate this process from the order of millions or thousands of years to a more relevant time frame? And that's when we get into computational research and materials informatics. So delving into this a little more deeply, as computational tools have advanced, they've been incorporated into the materials research process and pipeline. Um, with computational materials research, a lot of it is based in the physics of the way our materials work. So these physics-based models are used to predict structure, properties, and performance, and in turn find new candidates for lab testing. So it's an iterative process involving both a computational focus to identify what is a relevant material system to synthesize, and then synthesizing in the lab to get data to characterize your materials and then better inform your computational model. Getting into materials informatics, this is sort of used often in tandem in talking about computational materials research. It's definitely focused on the data-driven approach, where it's definitely impacted as well by the evolving of machine learning and artificial intelligence. With the advent of these technologies, there's been a shift toward using those tools to accelerate the process of materials discovery as well. So how does this all fit into quantum? Uh, I promise I won't get too far into the weeds with the physics of everything. I know that's not what everyone's strong suit is or what they're looking for here, but it is really important to understand sort of this fundamental background when it comes to considering materials research and using quantum computing for that purpose. So in general, one of the big advantages of quantum computing in materials research is that the understanding of core material structure properties arises from quantum physics and quantum mechanics. So the idea is to use quantum computing for chemistry and material science to enable humanity to tackle problems that are totally intractable on classical computers. And I think those who have attended these sessions for the last several weeks probably are now familiar with that as a common refrain, because a lot of the problems that we want to tackle, whether chemistry, pharmaceuticals, material science, are focused on those problems that are too challenging, too large for classical computing. One of the ways that there's a benefit from using quantum computing is that classical methods often get stuck in local minima when applying optimization methods, and quantum computing can avoid some of these limitations. So when we think about applying quantum computing to materials research, uh, it's fundamentally compatible because materials problems are very often quantum in nature and allow the combination of our physics-based models with observed data in a way that is overall more powerful than other traditional methods. Because of the trend with quantum computing, there will be exponentially higher computing power and data storage available using a quantum approach versus traditional classical computing. Getting a little bit deeper into the quantum advantages, we covered this a little bit on the last slide, but in general, it's better suited to complex simulation and modeling. So one of the reasons why we don't get stuck in those local minima is superposition and tunneling allow qubits to represent all of the possible final states and move from one configuration to another without getting trapped in local minima. In addition, thinking about the sort of trend in the long term with the incorporation of quantum computing more widely, um, there are modalities of quantum computing that allow for lower power demand for the same processing capability or for even higher processing capability based on the larger amount of information that can be stored with qubits versus classical bits. So as the technology matures for modalities that allow elevated temperature, lower energy operation, it definitely opens doors for far larger computational problems to be solved than would be possible just with your standard classical computing method. So I wanted to also emphasize this interesting symbiotic relationship between material science and quantum technology, where as materials discovery and development continues and progresses, this enables quantum technology, and quantum computing enables breakthroughs in material science. So it's this virtuous cycle that propels itself for additional breakthroughs and discovery. And thinking about the historical context for this, I love showing the image on the left. That is one of the initial silicon microchips by Fairchild. And it's something impressive to think about the timescale at which we have advanced in materials and the impact that that's had on our computing capacity. And this development is sort of the next step for this is in quantum computing. So thinking about everything from silicon microchip development as enabled by materials, this is also true of technologies like wide bandgap semiconductors for high power applications, light emitting diodes, RF devices, these sort of use cases where traditional silicon was not adequate on its own. And then getting into quantum computing, sensing, communication based on the various modalities of qubits. So we've talked about superconducting, trapped ion, neutral atom. These modalities are enabled by the materials research that has gone into developing those fundamental systems. And as part of this virtuous cycle, the simulation and modeling of quantum systems is enabling further development of quantum computing based on sort of looking at the underlying materials principles. So in general, I think we can probably safely say that material science is pretty integral to quantum computing development. And these insights that we're gaining from simulating these systems, from working on the fundamental architecture, is providing insights for qubit stability, control, performance. It's understanding that we get from the unique material properties of our quantum computing systems. So looking ahead in terms of materials discovery, I know a lot of you are interested in getting into the field of quantum technology, or you're already in the thick of it. So I challenge you to think about some of the problems that exist in material science as you're looking for use cases and applications for quantum. We can look at this overall as a sort of multivariate problem, not just in terms of like what are the elements of the periodic table that we can combine to get these materials, but what is the resulting atomic structure? What bonding scheme is stable with these elements? What are the effects of atomic vacancies in our lattice on the structure? And what do all of these sort of factors have as an impact on the properties of the materials that you're creating? So as you're thinking about these possible approaches, I wanted to touch on a few applications that are really relevant in the present day and will continue to be relevant for humanity as a whole, thinking about aviation, with every component of an airplane being made up of very specialty materials that are highly engineered for their purpose. In space applications, you're looking at extreme environments, so you want materials that are going to be radiation tolerant and can withstand thermal and pressure fluctuation, and the right materials for doing imaging and having robotics. In the biomedical field, we're thinking about materials for implants, hip replacements, knee replacements, you name it, medical devices, pacemakers, and then even the power sources that would go into medical devices, power sources that go into every other electronic that we use in the modern day. So with batteries and supercapacitors, hybrid capacitors, and alternative power sources to make sure that we are able to power all of the devices and computers to continue the breakthroughs we're working toward. So I'd like to leave off with a challenge to think outside of just the conventional material systems and look at to all of the possible combinations and consider how you can solve problems with our pretty expansive toolkit. And with that, I'd like to thank you all for your time and attention. Please feel free to reach out with any questions. And I have a list here of sources used for this presentation and reference materials. Thank you very much.
Wonderful. Allie, thank you. That was awesome. I always love how I learn something new every time I hear one of these presentations. I don't know if you all know, but there are quantum sensors that are nitrogen vacancy diamond sensors, and so it's used in biomaterials. There's so many things that these sensors are being used for. I even presented on neuroscience and quantum for defense applications of these sensors. And I tell you, the opportunities are endless here. For that, I say, if you are curious about anything, there are occasional unicorns that have that cross section of knowledge that you would like to know about. So please ask questions. If you're shy, ask them in the chat, ask them in Discord, and then we'll do our best to answer them for you.
Thank you, ma'am. It's a wonderful explanations about that materials and its development through quantum and again these materials innovations will be very much the innovations on that new materials discovery, all these things. And then I have one small doubt. Is there any possibility by using this quantum analysis to make into that a new kind of coating materials?
Sorry, could you repeat the last part of your question? What type of material?
No, I don't know, the lot of coatings, the material coatings, the cutting tool coatings, the different kinds of coatings are there.
Yes.
And yeah, we want to make into that very refined, perfect coating. Is it possible by doing some research on these materials and its costing
Yes,
on
this
the
gets
quantum
into
technology?
definitely. This gets into a really interesting sort of complex problem. When you're thinking about coating materials, it's effectively a combination of not only the material that you're using as the coating, but whatever substrate you want to deposit it on. So
Yes, sir.
it's the simulation of your layered structure and
Yes.
making sure that there's compatibility between what you have at the surface and what you have underneath. So this is the kind of problem that we're looking to continue computational and simulation based models to do a better job of sort of accelerating the research process rather than having to either blindly or based on heuristics decide on possible candidates, but potentially miss out on options that would be viable or better than what conventionally has been used.
Is it any possibility to reduce that imperfections on the crystallographic structure?
Right. I was actually reading a paper recently that was going over an application of mapping defects in a quantum-based system. So starting out with sort of a small unit cell structure or superlattice, and increasing the size of it and increasing the number of vacancies and changing the positions of those vacancies to model the effect of those defects on the final material properties. So it's definitely an active field of research, and something that I think will become only more relevant as time passes.
Thank you, ma'am. Thank you. Thank you for your patience
Awesome.
and thank you, ma'am.
Thanks for the question, Zinthil. Okay. Who is ready for hackathon? Now, I have been told that this hackathon is a little hard. I think it's really fun. Fabian helped me host a portion of it in Costa Rica. So, how about we all give it a try? Um, I think that sometimes when things are fun, it's a little bit more, enticing to try to figure them out. But I can you can tell me about it also. So here is Quantum Radar for Battleship game. This is what was proposed by Basque, which is a quantum company for it's a hackathon that was proposed by Basque for the Qiskit Fall Fest 2025. We had several options. Quantum protein folding, which I did not think would give us sufficient time to do, even if we started day one, and requires a lot of resources, which would be great if we if it was a situation in which that might be facilitated for everyone, and then we can play with it, trying to achieve some kind of algorithmic modification, but neither here nor there. We're going to talk about this one, the Quantum Radar for Battleship game. It is, I'm not sure if you played it or not, but what you try to do is give a location within the grid to see if you quote unquote blow up the ship of the other of the person, and you take turns by calling out the locations. So A, B, C, D, E, F, G, and then the positions of the rows. And so you would say B7 to target their opponent's ship. And if it contains the coordinate, then either you got the ship or you miss it. We are going to play within a variation here, which is more pacifist one, which is to find all ships with minimum chance of hitting them. Hence the radar implication of this. This Elitzer Weidman interaction-free bomb tester is a wonderful experiment that came about in 1993, and it confirmed how two principles of quantum physics, such as superposition and entanglement, can be harnessed to perform interaction-free measurements. As you can see here, there's some principles of light deflection. Sometimes this could be represented with, a Hadamard gate, as you know, is the splitting of the light beam. However, in this case, for the Max Zender interferometer, we are going, we're looking at the different states of alpha, and what we're going to do is to try to avoid the exploding the bombs rather than just exploding them, which is in the original experiment. So here is a modification of a bomb that collapses in superposition, and here is here is the different example where you could see the different states, right, where it does not explode. There is a very long mathematical justification and proving to this, which I do not invite you to go into. I invite you to think about the quantum circuit that could represent this. Now, the core principles here would be to avoid the bombs And over here, you can see that the interaction-free measurements are what we're looking for. So let's detect the bomb without hitting it. And the interaction that's being used over here is the angle rotation with the C naughts, right? And then we place the bomb and then we measure it. And then we have a detection. So this is, I don't know if you could see it well, but this is bomb found. There's a large amount of explosion, and then in this one, it doesn't explode. Then you upgrade the angle, and I'm not, and you can see here that you can diminish the amount of explosions with the bomb, the bomb explosions, and that you can detect the bomb with minimum explosions. And so what you're trying to do is make this measurement over here larger. As I mentioned before, you would be playing with the angles. Now, to play Battleship over here, we are going to be looking at, you could do it in a couple of ways. You could do it as the typical grid, which is 10 by 10, which I think is a lot of circuits and a lot of what's that called? Coordination, or we could do it 4 by 4. I'm gonna let you know by the end of this, because when we did it in a smaller grid, it's a lot of work. So for the time being, I'm not going to push you guys and ask for a 10 by 10. But I will say that it will be important to see how it measures against the different placements. And so you're looking here at the classical brute force plan and the quantum plan, which is in superposition. Like we said, you would give a location, right? A1. A1 would be here, or like, B2 or something like that, or C3 or D4, right? Or you could do A4. I think you know how to read grids. And so when you do use quantum superposition, you should be able to measure 75% of that score without with 8 measurements and not 6. So using the principles of superposition, you would be improving, right, your ability to detect the bombs. And so what we're going to do is stick to this 4 by 4 grid, and then I'm going to walk you through what it kind of looks like, just to give you a sneak peek. If you measure here in superposition, right, you need to, in classical brute force, you do 2 measurements and you only know whether it's here or here. With the measurements here, you would be able to see that the measurements across A2 and this 2 row, right? Or if you do like all in A, all in B, all in C, all in D, then how would you be, how are you linking those qubits in order to be able to measure them? I already gave you a clue above on some of the ways you can entangle the qubits, and this is one of the basics, knowing how you would entangle these qubits so you can have the positions. Now, the grid here itself can get pretty complicated if you're looking at it at a big point, but I'm going to give you a tip over here. Actually, maybe what I'll do, since it's only a day, is give you an example. Let me bring something over here to block this. You would need to create the following. And if I don't successfully cover my screen, then you get the answer. But that's okay. We'll do it as a speed and accuracy one. So here's the circuit. of how you would do a grid like that, okay? We're looking minimum for this result. And so ideally here, your score, even if you see the circuit, your score is going to depend on the detection over explosion times the measurements over brute force. And what I want you to know is that the angles between all of this are going to be really important. So ensure that you reproduce this circuit. Make sure you see the classical registers here and that you are able to make the measurements where they need to do, ensure that you've reproduced this properly, and then we can play Battleship. We we had a really fun time doing a small version of this, and it can you can if you work with this, you can work with small angle rotations, or you can work in like a canonical form, but just use the basis of the small angle rotations and know that the deadline is Wednesday. If someone solves it first and accurately, then you have more chances to win. If you solve it last and you are and you have the most number of bombs that are avoided, then that's great. I'm going to send you a template notebook. The measurements need to be the same. I'll just tell you right now, ChatGPT is not going to help you because I tried when I was doing it myself. And you have to be able to apply the qubits properly, use the angle rotations in a way where you can fine tune the 16, and then we will make sure that that bomb placement is the same for everyone. So please, 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 please do not modify the code of the illustration and the measurements, because that's going to be the baseline. And if you do, you will unfortunately be disqualified because there's not that much time to be able to. But like I said, use any AI you want. And if you want to be an overachiever and showcase how two people can play with it, then you are by all means invited to do so. I am going to pause and see if there are any questions. Does it make sense? Okay, and this is for the computing time that's been sponsored by QNow, and so we're gonna share a description with what that is, and we wish you the best of luck. So I'm going to share some of those images in the Discord channel to be able to help you with what you need to achieve, and I'm going to give you a basis with the notebook. Please call the quantum registers the same thing, and your classical registers the same thing, so we don't change the variables. If you feel ambitious and you want to get started now, like I said, give me minimum a number of, I'll tell you right now how many. If you do 10,000 shots, then do a minimum of, you need to get over 5,000 of no bombs exploded on a 16 qubit grid that has, well, it's actually 7 because it has an auxiliary qubit. But anyway, it's 16. Let's just say 16 qubit grid of a 4x4 with, you need to maximize the number of no explosions. If you do the measurements in the wrong place, you will get false inflated results, which is why I'm telling you, you need to ensure that you do it properly. And just play with the angle rotations until your circuit is well defined. And then we will make sure that the measurements, even if you just reproduce what we have here, then your submission who will be considered in the running. And again, whether if you make it better, you're doing great. Ensure that you do use the basis of the experiment. If you start changing gates, then you are not reproducing the Elitzur-Weitman experiment. We are playing, this is a quantum radar, so the placement of the bombs and all of that is also very important. Very well. There are no questions. Then I will stop the recording, and good luck to you all. Thank you very much for everything, and we will drop. Bye-bye.